In this lesson, we're going to be actually solving some exponential and logarithmic equations. So those of you that were kind of getting tired of the graphing over the past several lessons with growth and decay and then logarithmic functions, I think you'll like this lesson more. It's a lot more algebra heavy and step-by-step problem solving. But by the end of this lesson, you'll be able to solve exponential and logarithmic equations by equating bases. That's the first kind of example that we'll look at. And then also solve exponential and logarithmic equations by using the inverse relationship between exponential and logarithmic functions. And we've been talking about that since the last lesson, how exponential and logarithmic functions are inverses of each other. Like you can think of squaring and finding the square root of a number, inverse operations. As we go through this, still be thinking about how these functions model real-world problems and their solutions, and how do we equate bases. So this equating bases is very important, and that's the first kind of example that we're going to get into, which unfortunately will only work in certain cases. But in general, if two powers with the same base are equal, then their exponents must be equal. So let's look at that in algebraic terms. So for any b greater than 0, as long as it's not 1, if b to the x power is equal to b to the y power, then x has to equal y. And how we can use this is when we have an example like this first one here, where we have 25 and 125 as our bases. Now, those are not the same base. However, we can rewrite them so that they have the same base. So you should recognize that 25 and 125 are both powers of 5. So if I can rewrite this equation with a base as a power of 5 in both cases, then I can equate the exponents. So the first thing that I want to do is I want to rewrite 25 as 5 squared, and I still have to the x minus 1, and 125 will be 5 to the third power, 5 cubed, times 4x. Do not forget the exponents that you already have. Now I can simplify a little bit. So using distributive property, I have 5 to the 2x minus 2 power, and that'll be equal to 5, 3 times 4 is 12x. Now, according to this property, because my bases are the same, 5, then 2x minus 2 is going to be equal to 12x. My exponents are equal to each other because my bases are equal to each other, and I'm talking about an equation here. So I now have 2x minus 2 is equal to 12x, and now I can solve this just like any other two-step equation. So let me just rewrite this over here. 2x minus 2 is 12x, and I can subtract 2x from each side, and I have negative 2 is equal to 10x. Divide each side by 10, and negative 2/10 or negative 1/5 is equal to x. Now I should go back and check this. Now if this is true and this is a correct solution and it's not an extraneous solution, then if I plug negative 1/5 in for x and solve each side, I should get the same thing in both cases. And if I do that and I do the math, I end up with about 0.0210 for each side, and so that is a correct solution. The problem with this, which you may have already guessed, is that it's not always convenient to do that. It's not always going to be the case that you look at an equation and you see how you could rewrite that equation with the same base on either side. So we'll look at an example next where we don't have that, and we need to take a logarithm of each side. This example that we're going to look at is going to involve this change of base formula that we haven't really talked about yet. So what I want to do is get us started and then go back and write down the definition for the change of base formula and then incorporate it into the problem. So I have this problem, e to the negative x power is equal to 6. If you remember back to our last lesson on Intro to Logarithmic Functions, we talked about how eventually we would be able to figure out what exactly, if I'm talking about 2 to the x power is equal to 6. We said we know it's somewhere between 2 and 3, right? Because 2 squared is 4, 2 cubed is 8. So somewhere between 2 and 3 is going to be that value for x. But we didn't really know what it was. And so now we're going to figure out, in that kind of example, what exactly is the exponent. So let's look at this example of e to the negative x power is equal to 6. Now, I can't rewrite this conveniently to have the same base on either side. And we're talking about e here, which is going to be natural log. And we talked about a couple of properties in the last lesson about how if I take the natural log base e of e, those two would cancel each other out, and all I would be left with is the exponent, which is what I'm trying to figure out. So let me write down what I'm talking about. So if I take the natural log, and let me just write in the base e for now. Usually you won't see that, but just so you can see where this is all coming from. And then I still have that e to the negative x power, and I have to now do the same thing on the right-hand side. Now, these will cancel each other out. And so all I'm left with on the left is that negative x. So negative x. And here I have the natural log base e of 6. I want to show you the change of base formula because this will come up in some examples in your practice. When we're talking about change of base formula, we have u, b, and c that are positive numbers. B and c can't be 1. And so what we can say is log base c of u is going to be equal to log base b of u over log base b of c. For the most part, what you'll be seeing is if we have a log base c of u, that's going to be equal to log u over log c. And here we're talking about natural log, or sorry, common log, which is base 10. The other one is log base c of u is natural log u over natural log c. And then we're talking about base of e. Let me just give you a couple of number examples. So if I had, for example, log base 3 of 7, I could rewrite that as log 7 over log 3. Because that I actually can put into my calculator. I can use the log button. I'm no longer talking about a base that's something other than 10. So in this particular problem, I don't actually have to use this change of base formula, but I wanted to just show you what the setup would look like. So I could rewrite this, and I would have to if it were any other kind of number. But let me show you what I mean. I could rewrite this as natural log of 6 over natural log of e. Natural log of e, though, is just 1, so I don't need to do it in this case. I can just solve it by putting natural log of 6 into my calculator. if I do that, I get that negative x, which is is my exponent, is 1.792. And now if I check that by putting it into my calculator, e to the 1.792 power is 6.001. And I did a little bit of rounding there, so that 6.001 is absolutely fine. All right, let's look at one more example of taking a logarithm of each side. So in this problem, I have 10 to the 2x power plus 3 is equal to 8. This time and any time that I can simplify a little bit before I get started, I want to do that. So what I mean by that is I want to start by subtracting the 3 from each side. And now I have 10 to the 2x power is equal to 5. I'm going to take the log in base 10 of each side. And again, because we're just getting started with this, I'm going to write out the 10, but you definitely won't always see it. If you don't see a 10 there and you just see the log, you should assume it's talking about natural log base 10. But log base 10 times 10 to the 2x power is equal to log base 10 of 5. Now, same as with natural log, the log base 10 of 10, those will cancel each other out, and I'm just left with that 2x on the left-hand side. So I have 2x is equal to log base 10 of 5. And then I can go ahead and divide each side by 2 to finish. And so x is equal to log of 5, because that 10 doesn't have to necessarily show up. You know it's there, over 2. Now, if you are not able to use a calculator, you will be able to just leave your answer like this. However, if you have a calculator, you can go ahead and do the math, and you should get that x is equal to 349 thousandths. I would also get used to just writing your answer accurately to 3 decimal places. Most of what I've seen asks you to do 3 decimal places of accuracy. This is the end of part 1. In part 2, we are going to be looking at solving logarithmic equations. So for logarithmic equations, we have a property similar to exponential equations, and that's for logarithms with the same base. For any positive numbers, b, x, and y, and again, b cannot be 1, log b of x is equal to log b of y if and only if y is equal to x. Let's look at this first example of solving a logarithmic equation. So here I'm talking about natural log of both sides, and so this one's pretty easy to simplify. In this case, I have this equation where y is equal to x, and so I can just rewrite this as 4x plus 1 is equal to 2x plus 5. And now this is an easy equation to solve. I'm going to subtract 2x. And I'm going to subtract the 1, so 2x is equal to 4. Divide each side by 2, and x is equal to 2. If I want to go back and check this, I should put that 2 in where x is. So I have 4 times 2 plus 1, that would be natural log of 9, is equal to the 2 times 2 is 4 plus 5, natural log of 9. So this works as our solution for this first example. The next example that we're going to look at is exponentiating each side, or turning each side into an exponent. So if I look at this example, 4 times log to the base 3 of x is equal to 28. The very first thing that I want to do is simplify where I can. So if you see here, I have this 4 kind of hanging out on the side. I want to start out by dividing each side by 4, and that makes my math a lot easier. So I have log base 3 of x is equal to 7. And now this 3 tells me that I'm going to rewrite this by exponentiating each side so that it involves a power of 3. So I will start out by saying 3 to the log base 3 of x is equal to 3 to the 7th power. Just like every other example we've looked at, these will cancel each other out. And so all I am left with here is this x. So x is equal to 3 to the 7th power, and 3 to the 7th power is 2,187. Now, I want to make sure that this is correct, so I want to put that 2,187 in for this x, and think about logarithmic notation that we were talking about with the last lesson. I would have log base 3 of 2,187 equals 7. If I rewrite that to exponential notation to check myself, I would say 3 to the 7th power is that 2,187. Yes, so this answer is absolutely correct. In this final example, we're going to solve it and then check for extraneous solutions. So once we get a solution, we want to make sure that it actually works, that it's not that some of the solutions aren't true, or it's not that there isn't a solution. Now, when we do all of this algebra, we sometimes introduce these extraneous solutions into the process. And so we need to check at the end to make sure, either algebraically or if you have access to a calculator for that problem with the graph, just visually, to make sure that those solutions actually fall along the line that you've graphed. So if we're looking at this example, log base 8, quantity of 11 minus 6x, I have the same base on either side. So I can start out by just simplifying, and this one will be pretty straightforward. I have 11 minus 6x is equal to 1 minus x. Now, when I go to simplify this, I will get, I want to subtract 1, 10, and then I want to add 6x, so that's equal to 5x, and divide each side by 5, and x is equal to 2. And so that looks okay, right? We got a solution of 2. But now if I go back here and I plug that 2 in for these x's, I end up with log 8 of, that would be negative 1, is equal to log 8 of negative 1. The problem with this is that if I go back to my exponential notation, there is no power of 8 that will get negative 1 out. And so this one is no solution. As you go through these practice problems, really pay attention to the type of process that you're going to use to solve this. My first go-to would be to check to see if you can rewrite them both with the same base, but then if you can't, you're going to have to rewrite it using log or a natural log, or by exponentiating each side of the equation.